Okay, this is lesson 3.2, measuring the speed of light. And so in the first lesson, we would have had an introduction to electromagnetic radiation, otherwise known as EMR. And we know that that is accelerating charged particles or it's changing in magnetic or electric fields. And we were introduced to some new terminology. Some we've heard back in grade 8 and some is new now. One of the words that we learned, or two of the words we learned, is frequency and period. So period is the time it takes for one complete wavelength to pass. So if we're looking at a wavelength like this, it's the time for one complete wavelength to pass. This would be a period. Whereas if we were looking at frequency, it's the number of wavelengths in a measured period of time. So say this was in 1 second, we would have 1, 2, 3, 4 wavelengths in 1 second. So this is the difference between period and frequency, and we need to be able to float in and out of them and understand the difference between the two when we're talking about measuring the speed of light. So speed of light, or EMR travel, is constant, and it travels at the speed of light when it's in a vacuum or in air. It's the same value that we take into consideration. And so uniform is uniform if it stays in the same medium. So if that EMR is traveling in air all the time, or if it's in a vacuum, or if it's traveling in glass or in a diamond, then it stays the same until it moves out of a different medium. And so being able to figure out the speed of light wasn't necessarily easy. We know that the speed of light is 3.00 times 10 to the power of 8 meters per second. And so when we're looking at a number that large, it's incredibly hard to measure it. And it doesn't take long for it to go a long ways. So Galileo was the first scientist that decided he was going to try and measure this. And so what he did was he held a lantern and he covered it, and the person on the other hill would send a response back when he saw the light. And so Galileo thought along the same concept as triangulation. If he knew the distance between the two lamps, then he would be able to figure out the time, and he could measure the time from when he flashed it to when his assistant flashed him back, that he could figure out the speed of light. What he realized, though, is that there's too many human error pieces in there. It's a small time frame, and it's an incredibly large distance, and it relies too much on human response, which is delayed because it takes in the message of our brain to see the light, to tell ourselves to cover the light, and to flash it back. So then Ole Romer came along, and he figured out the speed of light based on the eclipse of one of Jupiter's moons. And so we look at orbital circular motion when we were in Physics 20. At certain times of the year, Earth and Jupiter are different distances from each other depending where they are in their orbits. But what he noticed was that there was a delay in the time he could see Jupiter eclipse one of its moons. And so he said that this difference had to be due to the different distances the light had to travel. And he had some rough ideas on the distance of the planets in orbit. He could figure out a rough calculation. And when we come down to today, so by today's standards, that number that he came up with was really not there, but it was the first attempt and ability to calculate an actual answer. So this is what we're talking about with the orbital piece. Here is the orbit that we have Earth going around the sun. And so there is a shorter distance between Earth and Jupiter's moon Io. And then it occurs later when it's on the other side of the sun. Then there was a fellow named Fizeau. He did a strong beam of light between the cogs of a spinning wheel. So that's the down parts of a gear. This is another word for a cog. Anyways, he traveled the light would travel through this cog, hit a mirror, it would come back up, and it would be reflected to the observer if the gear was spinning with the right period. So remember, period is how long it takes one cycle. One tooth of the gear would have exactly the right amount of time to move in the way of returning light. He was pretty accurate, and he only had about a 5% error measuring it this way. And so, though, in grand science fashion, somebody thought that they could improve that idea. And so Michelson used a spinning mirror apparatus. So this mirror here was rotated at a specific speed. And so what happened was he used an 8-sided mirror. And so you would have the light source would come in, it would hit one side of the mirror, it would bounce off this curved mirror, come back up on the other side, and then it would go to the viewer. So a beam of light hit one side of the mirror and reflected on a stationary mirror, and it bounced back. And what they knew was that this rotation of the mirror was 1/8 of a rotation. One side had flipped along into the correct position. So let's look at what this looks like. When Michelson did his experiment with the curved mirror 35 kilometers away, he found that the 8-sided mirror needed to spin at 3,200 RPM. So remember that RPM is revolutions per minute. Okay? And so this means when we look at number of revolutions per minute, this tells us that this value is frequency. So using this information, determine the speed of light. So the distance was 35 kilometers, and the frequency was 32,000 revolutions per minute. Now there's a couple of things that we have to do. We have to convert distance into meters. Meters is our base unit. So there's 1,000 meters in 1 kilometer. So we have 35,000 meters. And when we deal with any kind of unit, make note that this, when it says RPMs, is minutes, and we need seconds. That is our base unit in physics. And so when I know that I have, this is revolutions per minute. In 1 minute, there's 60 seconds. And so I get an answer of 533.3 revolutions per second, otherwise known as a hertz. Okay? So it's asking us to determine the speed of light. Right now, the only way we know how to solve light is velocity is equal to distance over time. We have this distance, but what we don't have is time. And what we do know is that the time is 1/8, because that's 1/8 of the revolution of the period, right? Because the period is the time it takes to complete that whole revolution. So for this point here, to go all the way around and back, that's 1 period. But when it just flips from here to here, that's 1/8 of that time frame. So we just need to look at 1/8. How do I get the period from this? Period is equal to 1 over frequency. Okay? So if we start the calculations for that, let's start. Period is equal to 1 over F, which is 1 over 533.33, because we need it in revolutions per second or in hertz. Our period is going to be equal to 0.001875 seconds. Time is going to be 1/8 of that, because this is the whole revolution. I need 1/8 of that revolution. And so we get 2.3437 times 10 to the negative 4 seconds. Now I can go and I can solve my velocity. It's equal to distance over time. One of the things that we need to pay attention to is that the time had to go this way and then it had to go this way. So the distance is actually times 2. That light beam actually traveled 70 kilometers. Okay, so the distance to the mirror and then from the mirror to the observer. And so our velocity is equal to and when I look at significant digits in the question, 2.99 times 10 to the 8 meters per second. And back in the day of Michelson's, this can be considered incredibly accurate. Okay, let's look at a second example. Using an experimental setup similar to Michelson's, using a 6-sided mirror, students found the speed of light to be 2.95 times 10 to the power of 8 meters per second. The mirrors replaced 45 kilometers from the fixed mirror. What was the frequency of rotation of the mirror? Let's look at what we know. We know the velocity to be 2.95 times 10 to the 8 meters per second. And we know the distance to be 45.0 kilometers. And it's asking us to find frequency. So in order to do this, we need to make sure that our distance is in meters. Okay, and so how do we solve for frequency? Frequency is solved by 1 over period. Okay, well, how do I know how to find period? Period is going to be equal to 6 sides times the time for one of those sides to rotate. When I figure that piece out, if I want time, I know that velocity is equal to distance over time. So let's work backwards. Time is equal to 45,000 meters. And remember, that's 45 kilometers to the fixed mirror, and it's 45 kilometers back out to the observer. So you're going to multiply that by 2. And then we're going to divide it by the velocity, 2.95 times 10 to the 8 meters per second, right? Because here we're isolating for time. Time is equal to distance over velocity. Time is going to be equal to 3.0508 times 10 to the negative 4 seconds. Once I have that, I can figure out the period. So period is equal to, it's six-sided, so 6 times what it takes to do one flip of the mirror. Because what's actually happening is you have your six-sided mirror, and that T is here and T is there. So if I want the total time it takes for this side to go all the way around and back again, I have to multiply it by the time by 6, one for each side. Period is going to be equal to 0.001835 seconds. Once I have period, frequency is easy to solve, 1 over period. So 1 over 0.001835 seconds. Frequency is going to be equal to 546.296 hertz. Hertz is the unit. This is revolutions per second. Hertz is the actual unit. And so when we do sig digs, we get the frequency of 546 hertz. So this six-sided mirror is spinning at 546 revolutions. So it's going around this circle 546 times in 1 second. Okay, we're going to pause it here. You're going to work on these questions at the bottom of the lesson, page 198, 10, 12, 14, 17, 20, 22, as well as these practice problems. As we go further into this unit, the concepts aren't super hard, but there's tons and tons and tons of math. So the more questions you practice now, the more fluent you will be in the language and in the ability to decode, and you'll be more successful later on in the unit.